Yes. All right. Thank you very much. Okay. I'm glad that you all found your way here. And it's been mentioned already, this is Comic Sans, which, as you know, is the official type font of awesome particle physics stuff. But in the interest of our mental sanity, I will keep it to other fonts. So from here on, Comic Sans is just a bad memory. Okay. Two things. First, the title, Breaking Baryons, which of course is an allusion to Breaking Bad, was inspired by the wonderful talk from last year, which was called How I Met Your Pointer, and which was also very successful, and you can check out that talk. I got the link there. And this talk goes especially well with another talk that we will have tomorrow by a real particle physicist, at least a bit more than myself. And it's called Desperately Seeking Susie. Which is about particle theories and the real cutting-edge physical questions. This is going to be happening tomorrow. All right, so we're going to start out with my talk, and I'm going to be talking about the questions of what are we doing, why, and what kind of stuff do we use. And I'm going to spend some time on explaining this last part, especially what is it that we do and how does this work. So what we do is we give a very high energy to small particles, which we call accelerating. But from a certain point on, from a certain level of energy, this doesn't really make sense because we don't actually make them go faster. Once they reach the speed of light, they can't go any faster. We just turn up the energy and the speed doesn't really change. This is technically useful, but it also gives rise to doubts about the term accelerating. But anyway, we'll just call it accelerating. There's two basic types of devices that you see there. You have storage rings, which are the circular facilities that most of you know. And then there's linear accelerators, which are in comparison very boring, so I'm not going to be talking about them a lot. We make the particles collide, which is the reason for giving them high energies. We want them to smash head on. And then this last part, which is about the most difficult thing, is we just see what happens, which is not at all as easy as it may sound. So why are we doing this? Well, you all know this formula, but I'm going to try and put it in terms which are a little bit closer to our hearts as we are here at Congress. And I might postulate that parts, like electrical parts, building parts, are actually the same as a device. Now, this is not quite wrong, but it doesn't feel exactly right either. I mean, if you have some parts and then you build a device from it, it's not the same. It's made of the same thing, but you do require a certain amount of conversion. You have a building process, you have specific rules how you can assemble the parts to make a device, and if you do it wrong, it will not work. And this is actually pretty similar to the notion of energy being equivalent to mass, because energy can be converted into mass, but it's not at all easy, and it follows a lot of very strict rules. But we can use this principle when we analyze how particle reactions are used to take a look at what mass and what energy forms there are. Now, suppose we are thinking about a device which is very, very rare, such as a toaster that runs NetBSD. Now, as you can see from the photo and from the fact that you see a photo, I'm not making this shit up. There is a toaster that runs NetBSD, but that's beside the point. Now, if we're particle physicists and we want to research this question, we know that parts are the same as a device. So if we just get enough parts and do the right kind of things to them, there might just turn out of nowhere a toaster that runs NetBSD. So let's give it a try. We produce collisions with technical parts, and if we do enough of it, and if we do it right, then there's going to be this result. Now, from these pictures you can see it doesn't seem to make a lot of sense. You will not get a toaster from colliding vehicles. But as far as particle physics go, this is the best we can do. I mean, we just smash stuff into each other, and we hope that some other stuff comes out which is more interesting. And that's what we do. So to put it in the technical terms, we use storage rings, which are this one circular kind of accelerator, to produce collisions, lots of them with high energy. And then we put some enormous experimental devices there, and we use them to analyze what happens. Now, first let's talk about these storage rings. This schematic view is what a storage ring is mostly made of, and you can see right away that it's not actually a circle. And this is true for any storage ring. If you look at them closely, they're not a perfect circle. You always have acceleration parts which are not actually curved. So we have the two basic elements of a curved part, which is just the curve, and then you have a straight part, which is there for acceleration. Now you have the separation. It would be nicer to have a ring, but it's much more easy this way. You have the acceleration where it is straight, and because it is straight, you don't need to worry about making the particles go on a curved path. So you can just leave out the magnetic fields. We need magnetic fields to keep them on a curve, but we need electrical fields to accelerate them. Now we could try and assemble these into one kind of device, a device that uses an electric field to accelerate the particles and at the same time uses a magnetic field to keep them on a curved path. Now this is the first thing that was tried. These kinds of accelerators were called cyclotrons, but they were very inefficient. You couldn't go to high energies. It was very difficult. So the evolution went to this way, where you just physically separate the two tasks. You have a straight part for acceleration, you have a curved part for the curve, and then that's much more easy. Okay, so let's take a look at the acceleration part of things. Now, you may know computer games where you go racing about, and then you have some kind of arrows on the ground, and if you go over them in the right direction, they make you faster. This is a kind of booster, if you will. Now, if you happen to go around the wrong way, and you go onto these arrows, they will slow you down, which makes sense because you're going the wrong way. You shouldn't be trying that. And this is the same effect we can think of when we think about what an electrical field does to a charged particle. If a charged particle moves through an electrical field in the right direction, so to speak, it will speed the particle up, taking energy from the field into the particle, making it go faster. But if we go the wrong way, then this particle will slow down, and it will give off energy. Now, if we were to try and, let's say we have a level editor, right? And we can edit this level where this little vehicle is going, and we want to make it go really fast. So what do? We just take this acceleration path, we just take these arrows, and we put them in a long line. Let's put 4, 5, 10 of them in a row. So if we go over them, we'll be really fast at the end. Now suppose the level editor does not allow this. It's just, by the rules of the game, it's not possible to put a bunch of arrows in a row. Which sucks, because then we can't really make them go really fast. But then we just ask an engineer who's got his shit together. And what is he going to suggest? You know what he's going to suggest. Can I hear it? Come on. Inverse the polarity. That's what he always does. So we inverse the polarity. And we're going to make our track look like this. So we have an arrow which gives us a boost in the right direction, and then there's an arrow in the wrong direction. Now, if we go over the track in this way, we'll speed up and slow down, and speed up and slow down. And in the end, we won't win anything. But here's where Jordi comes into play, because we'll be switching polarities at just the right moment. And if we switch polarities at the precise moment that we are in between two of these fields, then the next one will be an accelerating field. And it goes on and on like this. We always switch the direction of the arrows at the right moment when we are in between the two. And from the point of view of the vehicle, it will look like there's an accelerating field, followed by an accelerating field, followed by an accelerating field, which is the same as we tried to build, but which the game, or in the case of real accelerators, the universe, just wouldn't allow. So we're tricking the universe by using Jordi's tip and inversing the polarity at just the right moments. And this is what is done in particle accelerators, and this is called resonance frequency or radio frequency acceleration. Now this kind of device that you see there is the device that is used for this actual process in actual accelerators. It's about as big as a human child, but it weighs a bit more. It weighs several hundred kilograms. And in contrast to a child, it's made of a metal called niobium. Now niobium is a rare metal, but it's not super rare. And it fulfills 3 basic requirements that we have for these devices. It's ductile, which means you can easily shape it. Because you see that this shape is really weird. You got these kind of cone things going on, and they must be very precise. If these cones on the inside of the cavity are off by just micrometers, the whole thing won't work. So you need a metal which is which can be formed very well. Then you must be able to make it superconductive, to cool it down to a temperature where it will lose its electrical resistance. The electrical resistance will go down to almost 0, some nano-ohms is what's left. So that's the second requirement for this metal. And the third one is it shouldn't be super expensive. I mean, I guess you could use platinum or something, but then you couldn't pay for the accelerator. And as we're going to see, the accelerator is expensive enough as it is. So niobium is what's used for this kind of device. And as I said, we cool it down to about 4 kelvins, which is minus 269 degrees Celsius, or 4 degrees Celsius above absolute 0. and at this temperature, the electrical resistance of the metal is almost zero, which we need for the high-frequency fields that we put in. What we use to cool these things is liquid helium. So when they're in use inside the accelerator, they're not naked, exposed like you see here. They're enclosed by huge tanks, which are super tight and must hold on to large pressures and be super temperature efficient, very well insulating, because these must keep the liquid helium inside. But on the outside, there is the tunnel of the accelerator, and that's where people walk around. Not while the accelerator is running, but people walk around to do maintenance and stuff. So you must have a temperature differential between room temperature next to the accelerator and 4 Kelvin inside the tank where this cavity is sitting. So you have a temperature difference of 300 degrees, which this tank around the cavity must keep. So that's a very hard job. Actually, cooling is one of the more difficult things from an engineering point of view. Now, the thing which feeds the fields, the actual changing electrical fields, our polarity switch, into these cavities are called klystrons. There's a picture of a klystron. It's the longish device sitting on the bottom, and they're usually about as big as a refrigerator or two. And these klystrons produce radio waves, not very much unlike that which you hear in your car when you just turn on the radio. It's not modulated in the same way, so there's no sound information encoded, but it's extremely strong. You can see on the bottom that one of these klystrons, as it is in use in the LHC, has a transmitting power of 300 kilowatts. Now, if you think of the transmitting power of the Fernsehturm, like the Herzturm, which is right next, no, that way, which is right next to the conference center, or even the Fernsehturm in Berlin, it has about half the transmitting power of one of these klystrons. Now, for the LHC accelerator, 16 of them are used. So that's a lot of transmitting power. And because the power is so high, we don't actually use cables. Usually you transfer when you have some oscillator and you're checking out some signals, you just put cables between your source and your device. This is not what's used here, because cables get way too complicated when you have these high energies. So what is used is waveguides, and that's what you can see on the top there in this picture. It looks like an air duct, right? It looks like there's some sort of air conditioning system and the air moves through. That's not what it is. It is a waveguide which is designed to have the radio waves inside radiate in a certain direction. Think of a series of mirrors, long rectangular mirrors, and you put them all with the mirroring area inside. So you have a tube which is mirroring inside, and then at one side you shine in a bright light. Now the light can't escape anywhere, and it always hits the mirrors, so it goes on in a straight path. You've built yourself a waveguide for light. Now this clunky looking metal part is a waveguide, but for high frequency, high energy radio waves, which are fed into the cavities. And that's how acceleration happens. Now let's talk about the curves. This is where it gets less fidgety and more boom. So these devices you see here, there's two devices sitting next to each other, identical devices. These are the cryodipoles. Again, they have the word cryo in them because they're also cooled by liquid helium down to a temperature of about minus 270 degrees Celsius. They're 40 meters long, they weigh 35 tons, and each of these babies costs about 500,000 Swiss francs. And as you can see, one line above that, there is 1,200 of these curved dipoles in the LHC. So there you have a cost of $1.5 to $2 billion in the curved magnets alone. We're not talking acceleration, we're not talking about power use, we're not talking about the helium that you need for the cooling or the power that you need for the cooling. It's just building these things, just building the curve, 27 kilometers. And that's what you have there as a cost. Now, what they do is they make a huge magnetic field, because in a magnetic field, a charged particle will go on a curve. That's what we want, right? But to make these particles with a very high energy and keep them on a tight curve, now in particle physics terms, let's say that 27 kilometers to go around one way is a tight curve, we need a current of 12,000 amps, which is a large current that goes through these dipoles, which is the reason why we have them superconductingly cooled, because otherwise you put 12,000 volts, you put 12,000 amps through a piece of metal and it just melts away. You don't get a magnetic field, maybe for a microsecond or two. But you want to sustain a stable field of 8.5 Tesla to make these protons go around on a curve. So yeah, that's a big thing. Now there's also niobium in there. Not the big clunky parts like the cavity we saw, but thin niobium wires, actually half niobium, half titanium most of the time. But since there's so many magnets and this is so long a curve, there is 600 tons of atomic niobium in this entire accelerator thing. And this was a fourth of the world production of niobium, which comes mostly from Brazil, by the way. This was a fourth of the world production of niobium for 5 years. So that's where it all went. It just went into the accelerator. And now if we have this running, okay, we have it up, we have it cooled, we have a large current going, we got our nice big magnetic fields, and there is energy stored. I mean, we put in a lot of power, and the magnetic fields are up, and they are stable, and that means there is magnetic energy stored in this. And the amount of energy that is stored in the curved magnets alone of the LHC when it's running is 11 gigajoules. Now, sounds like a lot. Let's compare it to something. If we have an absurdly long freight train with, let's say, 15,000 tons. I hear that normal freight trains in Germany or England have about 5,000 tons. So let's take a big freight train and multiply it by 3. If this freight train goes at 150 kilometers per hour, then the kinetic energy, the movement energy of this train is equivalent to the magnetic energy that is stored in the LHC. And that is why we don't want any problem with the cooling. Because if we get a problem with the cooling, bad things happen. This is a photograph of what at CERN at the LHC they just call the incident, which was a tiny mishap that happened just a few weeks after the LHC was taken into operation for the first time in 2008, and it shut the machine down for about 8 months. So that was a bad thing. And it's a funny story. When they were constructing these magnets, now what you see here is the connection between two of these magnets. I told you that each of them weighs 35 tons. So here you have a connection between two parts that are 35 tons in weight each. And they're shifted by almost half a meter. So it takes a bit of boom. So what happened was the cooling broke down and the helium escaped, and the sheer force of the helium expanding, because if you have liquid helium and it instantly evaporates into gaseous helium, then the volume multiplies by a very large amount. And what they had was, what I hear is that the tunnel of the LHC, which has a diameter of about, let's say, 6 or 7 meters, was filled with nothing but helium, which pushed away the air for about 100 meters around this incident. So the helium evaporated, it pushed everything away, it made everything really cold, some cables broke and some metal broke. And the funny thing now is, the engineers that built the LHC, before they did that, visited Hamburg, because here there is a particle accelerator which is not quite as large. See, the LHC has 27 kilometers. Here in Hamburg we have a particle accelerator called Hera, which had 6.5 kilometers. So it's the same ballpark, it's not as big. And in Hera they had a safety system against these kinds of cryo failures. They're called quenches. They had a protection system which protects this exact part. Now we're talking about, yeah, like how should we build this? Should we have a quench protection at the connection between the dipoles? And the Hera people in Hamburg said, well, we have it, and it's a good thing. You should leave it out if you build the LHC. Well, they left it out. They ran out of time. They ran out of money. The LHC project was under pressure. Because they had promised to build a big machine by that time and they weren't really finished, so they cut some edges. Well, this was the edge they cut, and it cost them 8 months of operation, which says that they really should have listened to the people of Hamburg. Okay, so in summary, the operation of the storage rings, we can just say this. They get perfectly timed kicks with our polarity switching at just the right moment by radio waves generated in these large klystrons from the funny-looking metal tubes that we called cavities. And some big-ass superconducting magnets keep them on a curve when they're not being accelerated. Now the trick is, one of these kicks, like moving through the cavity once, may not give you all the energy you want. In fact, it doesn't. But if you make them go around in the ring, they come by every couple of nanoseconds. So you just have them run through your acceleration all the time, which is the big difference between a storage ring and a linear accelerator. A linear accelerator is basically a one-shot operation. But here, you just give them an energy kick every time they come around, which is often, and we're going to see that. So that's a summary of what the storage rings do. Now, the machine layout, if you look at a research center which has a bunch of accelerators, it almost always goes like this. you have some old, small storage rings, and then they built newer ones, which were bigger. So this is just a historical development. First you build small machines, then techniques get better, engineering gets better, you build bigger machines. But you can actually use that. It's very useful. Because the older machines you can use as pre-accelerators. For a variety of reasons, it's useful to not put your particles in with an energy of 0 and then have them accelerate up to the energy you want. You want to pre-accelerate them, like make them a little faster at a time. And that's what you do. You just take the old accelerators. And if we look at the accelerator layout of some real-world research centers, you can actually see this. On the left you have CERN in Geneva, and on the right you have DESY here in Hamburg. And you can see that there are smaller accelerators, which are the older ones, and you have bigger accelerators, which are connected to them. And that's this layout of the machines. Okay, now let's talk about collisions. This is a nice picture of a collision. It's not actually a proton collision, but a heavy ion collision, which they do part of the time in the LHC. They are extremely hard to produce. We're going to see that, but still, we make an awful lot of them. So let's see. First of all, let's talk about what the beam looks like, because we're going to be colliding beams. So what are these beams? Is it a continuous stream of particles? Well, it's not. Because the acceleration that we use, these radio frequency polarity shifting mechanisms, they make the particles into bunches. So you don't have a continuous stream, you have separate bunches. But how large are these bunches? Is there one particle per bunch? You got a particle, you wait a while, there's another particle. Well, it's not like that. Because if it were like that, if we had single particles coming after one another, it would be impossible to hit them. You have to aim the beams very precisely. I mean, think about it. One comes around 27 kilometers around the ring. The other comes around 27 kilometers going the other way, and now you want them to hit. You have to align your magnets very precisely. You can think of it like this. You have a guy in Munich and you have a guy in Hamburg, and they each have a rifle. And the bullets of the rifle are, let's say, 1 centimeter in size. So the guy in Hamburg shoots in the air, and the guy in Munich shoots in the air, and they're supposed to make the bullets hit in the middle over, let's say, Frankfurt. Which they're not going to manage, and which is actually way too simple. Because if the bullet is really 1 centimeter in size, then the equivalent distance that the two shooters should be away from each other, if we want to make it the same difficulty as these protons, would not be between Hamburg and Munich. It would be from here to fucking Mars. I calculated that shit. We don't even have rifles on Mars anyway. So what we got is we got large bunches, very large bunches. And in fact, there's 10 to the 11 protons per bunch, which is 100 billion. This is where I call Sagan you going millions of millions. Okay, so we got 100 billion protons in one bunch, and the bunches go by one after the other. Now, if you stand next to the LHC and you were capable of observing these bunches, you would see one fly by every 25 nanoseconds. So you go, there's a bunch. Now it's 25 nanoseconds, there's the next one. And there's about 7.5 meters between the bunches. Now, 7.5 meters corresponding to 25 nanoseconds, you see that the speed is very big, and indeed it's almost the speed of light. We we accelerate them, and at some point they just go with the speed of light, and we just push up the energy, we don't make them go any faster actually. And if you were to identify the bunches, which actually you can, you would see that there are 2,800 bunches going by. And then when you have number 2,809, that's actually the first one that you counted, which has come around again. Per direction. So in total we have over 5,000 bunches of 100 billion protons each. So that's the beam we're dealing with. Oh, and a funny thing, you get charged particles moving, it's actually a current, right? In a wire, you have a current running through it, there's electrons moving or holes moving, and you get a current. If you were to measure the current of the LHC, it would be 0.6 milliamps, which is a small current. But we're doing collisions anyway and not power transmission, so that's fine. Now, this is a diagram of what the actual interaction point geometry looks like. You get the beams from different directions. Think of it like the top one coming from the right, the bottom one coming from the left, and they are kicked into intersecting paths by magnets. You have very complicated, very precise magnetic fields aligning them so that they intersect. And it's actually it's a bit of a trying out game. I've heard this from accelerator operators, is that you shift the position of the beams relative to each other by small amounts, and you just see where the collisions happen. You go like, oh yeah, okay, there's lots of collisions. Oh no, they're gone. I'm going back. And it's just, you do it like that. You can save the settings and load them and calculate them, but it's actually easier to just try it out. Now, if we think of how much stuff we've got going on, you got a packet, a bunch of 100 billion protons coming one way, you got another packet of 100 billion protons coming the other way. Now the interaction point area is as small as a cross-section of a human hair. You can see that, it's a hundredth of a square millimeter. Now how many collisions do you think we have? We got, it's not that bad, yeah. We got about 20 in the LHC. And the funny thing is, people consider this a bit too much. The effect is called pileup. And the bad thing about pileup is you got beams intersecting, you got bunches crossing is what we call it. And there's not just one collision which you can analyze, but there's a bunch of them, around 20. And that makes it more difficult for the experiments. We're going to see why. Well, and if we have 20 collisions every bunch crossing, and the bunches come by every 25 nanoseconds, that gives us a total of 600 million collisions per second, per interaction point, which we don't have just one of. We have 4 experiments. Each experiment has its own interaction point. So in total, we have about 2 billion proton-proton collisions happening every second when the LHC is running. Now let's look at experiments. Yeah, this is a photograph of one part of the ATLAS experiment being transported. And as for the scale of this thing, well, in the physics community, we call this a huge device. I have a diagram of the experiment where this is built in, and you're going to recognize the part, which is the one I've circled there. So the real thing is even bigger. And down at the very bottom, just to the center of the experiment, there's people, which, if I check it like this, they're about 15 pixels high. So that's the scale of the experiment. The experiment has the interaction point at the center. So you got a beamline coming in from the left, you got the other beamline coming in from the right, and in the very core of the experiment is where the interactions, where the collisions happen. And then you got the experiment in layers like an onion, going around them in a symmetrical way. Inside you have a huge magnetic field, which is almost as big as the curve magnets we were talking about when I was describing the storage ring. This is about 4 Teslas. So it's also a very big field. But now we've got a 4 Tesla field, not just over the beam pipe, which is about 5 centimeters in diameter, but through the entire experiment. And this thing is like 20, 25 meters. So you got a 4 Tesla field, which should span more than 20 meters. And just for shits and giggles, it's got 3,000 kilometers of cables, which is a lot. And if you just pull some random plug and don't tell anyone which one it was, you're making a lot of enemies. Okay, so the innermost thing is what we call the inner tracking. It is located just centimeters off the beamline. It's supposed to be very, very close to where the actual interactions happen. And this thing is made to leave the particles undisturbed. They should just fly through this inner tracking detector, and the detector will tell us where they were, but not actually stop them or deflect them. This gives us precise location data as to how many particles there were, what way they were flying, and from the curve, what momentum they have. Outside of that, we've got calorimeters. Now these are supposed to be stopping the particles. A particle goes through the inner tracking without being disturbed, but in the calorimeter it should stop. And it should deposit all its energy there, which is why we have to put around it the inner tracking. You see, if we put the calorimeter inside, it stops the particle. Outside of that, nothing happens. So we have the calorimeters outside of that. And then we got these funny wing things going on. That's the muon detectors. They are there for one special sort of particle out of the 50, let's say 60, depends on the way you count, elementary particles that we have. These large parts are just for the muons. Because the muons have the property, the tendency to go through all sorts of matter undisturbed. So you just need to throw a huge amount of matter in the way of these muons, like let's have a brick wall and then another one. And then you may be able to stop the muons or just measure them. Okay, this is to give you an idea of the complexity of the instrument on the inside. Now this is the inner tracking detector. It's called the pixel detector. And you see guys walking around in protective suits. Now it's not for fun or just for the photo. This is a very, very precise instrument, but it's sitting inside This huge experiment, which, again, I calculated that shit, is about as large as a space shuttle and weighs as much as the Eiffel Tower. And inside, they've got electronics, they've got almost a ton of electronics, which is so precise that it makes your smartphone look like a rock. So there you go. It's a very, very complicated sort of experiment. Now, let's talk about triggering, because as I said, there's 600 million events happening inside this. That's 40 million bunch crossings. Now, how are we going to analyze this? Is there a guy writing everything down? Well, obviously not. So this experiment with all the tracking and the calorimeters and the muons and everything has about 100 million electronic channels. And one channel could be the measurement of a voltage or a temperature or a magnetic field or whatever. So we got 100 million different values, so to speak. And that makes about 1.5 megabytes per crossing, per every event readout, which gives us, multiplied by 40 million, gives us about 60 terabytes of raw data per second. That's bad. I looked it up. I think the best RAM you can do is about 1 terabyte per second or something. So we're obviously not going to tackle this by just putting in fast hardware, because it's not going to be fast enough. Plus, the reconstruction of an event is done by about 5 million lines of C++ code, programmed by some 2,000 or 3,000 developers around the world. It simulates for one crossing 30 million objects, which is the protons and other stuff flying around, and it is allocated to take 15 seconds of one core's computing time. Now, to calculate it all, you would need about 600 million cores. That's not happening. I mean, even if we took over the NSA and used all their data centers for LHC calculations, it still wouldn't be enough. So we have to do something about this huge mass of data. And what we do is we put in triggers. Now, the trigger is supposed to reduce the number of events that we look at. It looks at the first level trigger, looks at every collision that happens. And it's got 25 nanoseconds of time to decide, is this an interesting collision? Is it not an interesting collision? And we tell it to eliminate 99.7% of all collisions. So only every 400th collision is allowed for this trigger to go, oh yeah, okay, that looks interesting, let's give it to level 2 trigger. So then we end up with about 100,000 events per second, which gets us down to 150 gigabytes per second. Now, we could handle this from the data flow, but still we can't simulate it. So we got another level trigger. This is where the two experiments at the LHC differ. The CMS experiment has just a level 2 trigger, does it all there. The Atlas experiment goes the more traditional way. It has a level 2 trigger and a level 3 trigger. In the end, these combined have about 10 microseconds of time, which is a bit more. And it gives them a chance to look at the events more closely. Not just, let's say, was it a collision of 2 protons or of 3 protons? Were there 5 muons coming out of it, or 3 electrons and 2 muons? This is the sort of thing they look at. And certain combinations, the triggers will find interesting or not. Let's say 5 muons, I don't give a shit about that. 3 muons and 2 electrons, all right, I want to analyze it. So that's what the trigger does. Now, this level 2 and 3 trigger, again, have to kick out about 99.9% of the events, and they're supposed to leave us with about 150 events per second, which gives a data volume of a measly 300 megabytes per second, and that's something we can handle. We push it to computers all around the world, and then we get the simulations going. Now, this is a display. This is what you see in, let's say, in the media. If you take one of these events, just one, of the interesting events which actually reach the computers, because those 40 million bunch crossings, well, most of them don't reach the computers, they get kicked out by the triggers. But out of the remaining 100 or 200 events per second, let's say this is one. It's an actual event, and it's been calculated into a nice picture here. Now, normally they don't do that. It's analyzed automatically by code, and it's analyzed by the physics data, and they only make these pretty pictures if they want to show something to the press. To the left, you have what's called a Feynman diagraph. That's just a fancy physical way of saying what's happening there. And it involves the letter H on the left side, which means there's a Higgs involved, which is why this event was particularly interesting to the people analyzing the data at the LHC. And you see a bunch of tracks. You see the yellow tracks all curled up inside. That's a bunch of protons hitting each other. And the interesting thing is what happens, for example, above there with the blue brick kind of things. Now there's a red line going through these bricks. This indicates a muon. A muon which was created in this event there in the center, and it went out, and the bricks symbolize the way the reaction was seen by the experiment. There was actually just a bunch of bricks lighting up. Right? You got, I don't know, 500 bricks around it, and brick number 237 says, whoop, there was a signal. And you go, all right, might have been a muon moving through the detector. When you put it all together, you get an event display like this. Okay, so we got to have computers analyzing this. And with all the 4 experiments running at the LHC, which is not just CMS and Atlas I mentioned, but also LHCb and Alice, they produce about 25 petabytes of data per year. And this must be, it cannot be stored at CERN alone. It is transferred to data centers around the world by what is called the LHC Optical Private Network. So they've got a network of fibers going from CERN to other data centers in the world. And it consists of 11 dedicated 10 gigabit per second lines going from CERN outward. If we combine this, it gives us a little over 100 gigabits of data throughput, which is about the bandwidth that this Congress has. Which is nice, but here it's dedicated to science data and not just porn and cat pictures. From there, it's distributed outward from these 11 locations to about 170 data centers in all the world. And the nice thing is, this data, this 25 petabytes per year, is available to all the scientists working with it. There's about, well, everybody can look at it, but there's about 3,000 people in the world knowing what it means. So all these people have free access to the data. You and I would have free access to the data, just thinking it's cool to have a bit of LHC data on your hard drive, maybe. All in all, we have 250,000 cores dedicated to this task, which is formidable, and about 100 petabytes of storage, which is actually funny because 25 petabytes of data are accumulated per year, and the LHC has been running for about 4 years. So you can see that they buy the storage as the machine runs, because 100 petabytes, okay, that's what we have so far. If we want to keep it running, we need to buy more disks. Right. Now, what does the Velociraptor say about the triggers? If the triggers are supposed to eliminate those events which are irrelevant, which is not interesting, well, who tells them what's irrelevant? Or to put it in the terms of conspiracy Keanu, what if the triggers throw away the wrong 99-point-something% of events? I mean, if I say, if there's an event with 5 muons going to the left, kick it out. Well, what if that's actually something that's very, very interesting? How should we tell? Well, we need to think about this very precisely, and I'm going to tell you about an example in history where this went terribly wrong, at least for a few years. We're talking about the discovery of the positron. The positron is a piece of antimatter. It is the anti-electron. It was theorized in 1928 when theoretical physicist Dirac put up a bunch of equations, and he said, there should be something which is like an electron, but has a positive charge. Some kind of antimatter. It's not what he said, but that's what he thought. But it was only identified in 1931. They had particle experiments back then. They were seeing tracks of particles all the time, but they couldn't identify the positron for 3 years, even though it was there on paper. So what happened? Well, you see the picture on the left. This is the actual, let's say, baby picture of the positron. I'm going to build up a scheme on the right to show you a bit more, to give you a better overview of what we're actually talking about. In the middle you have a metal plate, and then there's a track which is bending to the left, which is indicated here by the blue line. Now if we analyze this from a physical point of view, it tells us that the particle comes from below, hits something in the metal plate, and then continues on to the top. So the direction of movement is from the bottom to the top. The amount by which its curvature reduces when it hits the metal plate tells us it has about the mass of an electron. Okay, so far so good. But then it has a positive charge because we know the orientation of the magnetic field, and that tells us, well, if it bends to the left, it must be a positive particle. So we have a particle with the mass of an electron, but with a positive charge, and people were like, what? So then someone ingenious came up and thought of a solution. They developed the picture the wrong way around. It's what they thought. Well, it's wrong, of course. There is such a thing as a positron. And it's like an electron, but it's positively charged. But, well, to put it in a kind of summary maybe, you can only discover that which you can accept as a result. Now, this sounds like I'm Mahatma Gandhi or something, but it's just what we call science. Okay, so to recap, what have we seen, what have we talked about? We saw from the basic principle that if we have energy in a place, then that can give rise to other forms of matter, which I call parts equal a device. You get a lot of parts, you do some stuff, out comes a device. We have storage rings, which give a lot of energy to the particles, and in which they move around in huge bunches, billions and billions of protons in a bunch, and then colliding. Which gives us, in the huge experiments that we set up, an enormous amount of data, ranging in the terabytes per second, which we have to program triggers to eliminate a lot of the events and give us a small amount of data which we can actually work with. And then we have to pay attention to the interpretation of data so that we don't get a fuck up like with a positron, which is a very hard job. And I hope that I could give you a little overview of how it's fun. And it's not just, you see, it's not just about building a big machine and saying, I've got the largest accelerator of them all. It's a collaborative effort. It's literally thousands of people working together. And it's not just about two guys getting a Nobel Prize. You see this picture on the top left? That's about 1,000 people at CERN watching the ceremony of the Nobel Prize being awarded, because everybody felt there's two people getting a medal in Sweden. But it's actually an accomplishment, it's actually an award for everybody involved in this enormous thing. And that's what's a lot of fun about it. And I hope I could share some of this fascination with you. Thank you a lot. Before we get to Q&A, I'm going to be answering questions that you may have. My name is Michael. I'm MTU on Twitter. I've got a DECT phone. I talk about science. That's what I do. I hope I do it well. And you can see the slides and leave feedback for me, please, in the event tracking system. And tomorrow, if you have the time, you should go watch the Desperately Seeking Susie talk, which is going to be talking about the theoretical side of particle physics. Okay, that's it for me. Now on to you.
Okay, if you have questions, please line up. There's a mic there and a mic there. And if you're on the stream, you can also use ISC and Twitter to ask questions. So I'm going to start here. Please go ahead.
Okay, thanks a lot. It was very fascinating and talk and nice to listen to. My question is, did Hera ever suffer a quench event in which the quench protection saved the infrastructure?
No, actually it didn't. There were tests where they provoked a sort of quench event in order to see if the protection worked, but even if this test would have failed, it would not have been as catastrophic. But there were failures in the operation of the Hera accelerator, and there was one cryo failure, which is actually a funny story, which is where one part of the helium tubing failed, and some helium escaped from the tubing part and went into the tunnel. Now what happened was that the air moisture, just the water in the air, froze at this point, and the technical director of the Hera machine told us this at one point. He sat there with a screwdriver and a colleague picking off the ice of the machine for half the night before they could replace this broken part. So yeah, cryo failures are always a big pain.
Do we have questions from the internet? Okay.
Yeah, I have one question. That is, how are the particles inserted into the accelerator?
Yeah, they mostly start in linear accelerators. Oh no, wait, we got it here. So you got the series of storage rings there at the top in the middle, and you have one small line there. That's a linear accelerator. To get protons is actually very easy. You buy a bottle of hydrogen, which is just a simple gas you can buy, and then you strip off the electrons. You do this by ways of exposing them to an electric field, and what you're left with is the core of the hydrogen atom, and that's a proton. Then you accelerate the proton just a little bit into the linear accelerator, and from there on it goes into the rings. So that means basically at the start of these colliding experiments is just a bottle of helium that somebody puts in there. And at the LHC it's about, I mean, you know a gas bottle, it's about this big and it weighs a lot. At the LHC, they use up about 2 or 3 bottles a year for all the operations, because a bottle of hydrogen has a lot of protons in it.
You, please, over there.
Actually, I have 2 questions. One part is, you said there are 2 beams moving in opposite directions, and you explained the way where you switch polarity. How can this work with 2 beams opposing each other?
Yes, that's a good question. Now, if I show you the picture of the cryodipole, you will see that these 2 beams are not actually in the same tube. There we go. There we go. You see a cryodipole, and on the inside of this blue tube, you see that there's actually 2 lines. You can't see it very well, but there's 2 lines. So they're inside the same blue tube, but then inside that is another small tube, which has a diameter of just about, well, a Red Bull bottle, let's say 5 or 6 centimeters in diameter, and this is where the beam happens, and these are just sitting next to each other. So the beams are always kept separate, except from the interaction points, where they should intersect. And the acceleration happens obviously also in separate cavities.
Yes.
You had a second
the
question.
Second question is, with the experiments, where are they placed? On the curve or on the acceleration part? Or?
The interaction points are placed between the acceleration on the straight path, because again, it's much easier if you had the protons going straight for 200 meters, then you can more easily aim the beam. If they come around a curve, then they have a curve motion, you need to cancel that. That would be much more difficult.
And the left, please.
Okay, so you get yourself a nice storage ring, and then you connect it to the power plug, and then your whole country goes dark. Where does the power come from?
Well, in terms of power consumption of, let's say, households, cities, or aluminum plants, accelerators actually don't use that much power. I mean, most of us don't run an aluminum plant, so we're not used to this sort of power consumption. But it's not actually all that big. I can tell you about the Hera accelerator that we had here in Hamburg, which I told you is about 6.5 kilometers, not the 27, so you can sort of extrapolate from that. It used, with the cryo and the power current for the fields and everything, it used about 30 megawatts. Now 30 megawatts is a lot, but it's not actually very much in comparison to, let's say, aluminum plants or large factories. But in fact, the electricity cost is a big factor. Now you see the LHC is located at the border between Switzerland and France. It gets most of its power from France. And you always have an annual shutdown of the machine. You always have it off about 1 or 2 months of the year, where you do maintenance, where you replace stuff, you check stuff. And they always take care to have this shutdown for maintenance in winter, because they get their power from France. And in France, many people use power for heating. There's not gas heating or long distance heat conducting pipes like we have in Germany, for example. The people just use power for heat. And that means in winter, the electricity price goes up by a large amount. So they make sure that the machine is off in winter when the electricity price is up, and it's running in the summer where it's not quite as bad. So it's a factor if you run an accelerator, and you should tell your local power company if you're about to switch it on. But actually, it won't make the grid of even a small country like Switzerland break down or anything.
Do we have more questions from the internet? Internet? No internet. Okay, then just go ahead. Firefox guy.
So you see a lot of events, and I guess there's many wrong ones too. How do you select if an event you see is really significant?
Well, you have different kinds of analyses. Like I told you, there's 100 million channels you can pick from. With the simplest trigger that you have, the level 1 trigger, it can't look at the data in much detail because it only has 25 nanoseconds. But as you go higher up the chain, as the events get more rare, you can look at them more closely. And what we end up in the end, these 100, maybe 200 events per second, you can analyze them very closely. And they get a full-out computation. You can even make these pretty pictures of some of them. And then it's basically, well, theoretical physicists' work to look at them and say, well, this might have been that process, but still a lot of them get kicked out. When the discovery of the Higgs particle was announced, it was about 1.5 years ago, well, the machine had been running for 2.5 years. And like I told you, there's about 2 billion proton collisions per second. Now, the number of events that were relevant to the discovery of the Higgs events, it was not even 100. out of 2 billion per second for 2.5 years. So you have to sort out a lot because it's very, very, very rare. And that's just the work of everybody analyzing, which is why it's a difficult task done by a lot of people.
Right, please.
What I'm interested in, you say 1 year of detector running. How much time it is here does this detector actually run? Is it actually running?
Well, yeah, like I said, we have the accelerator off for about 1 or 2 months. Then if something goes wrong, it will be off again. But you want to keep it running for as long as possible, which, well, in the real world, let's say it's 9 months a year. That's about it. Straight through. Well, not in a row, but it's always on at least for a week. And then you get maybe a small interruption for a day or two, but you can also have a month of straight operation sometimes.
Internet, please.
Yeah, another question. What would happen if they actually find what you are looking for? Throw we the LHC in the dumpster, or what do we do?
That's a good question. It would be one hell of a waste of a nice-looking tunnel. And you might consider using it for, I don't know, maybe swimming events or bicycle racing. Well, but actually, yeah, that's a very good question, because the tunnel which the LHC sits in, this 27-kilometer tunnel, it was not actually dug, it was not actually made just for the LHC. There was another particle accelerator inside before that. It had less energy because it didn't accelerate protons, but just electrons and positrons. That's why the energy was a lot lower. But they said, well, okay, we're going to build a very large accelerator. Does anyone have a 30-kilometer tunnel maybe? And then CERN came up with, yeah, well, we got this 27-kilometer tunnel where this LEP accelerator is sitting in, and when it's done with its operations in, I don't know, by that time, let's say in 10 years, we're going to shut it off. Why don't we put the next large accelerator in there? So you try to reuse infrastructure, but of course you can't always do that. The next huge accelerator, if we get the money together as a science community, because the politicians are being a bitch about it, if we get the money, it's going to be the International Linear Collider, and that's supposed to have 100 kilometers of particle tubes, and, well, you need to build a new tunnel for that, obviously.
First off, couldn't you use it in something like material sciences, like example with DESI? Well, okay, if you are done with leptons, you can still use it for a synchrotron laser or something like this.
That was thought of. The Hera accelerator at DESI was shut off, and people were thinking about if they could put a synchrotron machine inside it. But the problem there is the Hera accelerator is 25 meters below the ground. There's just not enough space. With particles accelerating, you just need a small tube. But for synchrotron experiments, you need a lot of space. So you would have to enlarge the tunnel by a lot, and this was not worth it in the case of the Hera accelerator. But interestingly, one of the pre-accelerators of Hera, one that was older, is now used for synchrotron science, which is Petra, which used to be just an old pre-accelerator, and now it's one of the world's leading synchrotron machines. So yeah, you try to reuse things because they were expensive.
And may I just ask another question? You said you you use just the matter from a bottle of hydrogen or a bottle of helium. Well, most helium or hydrogen is protons, or in the case of helium, helium-4, but you have a little bit helium-3 or deuterium. And well, you are looking for interesting things you don't expect. So how do you differentiate if it's really something interesting, or, oh, one of those damn deuterium nucleus again?
You don't get wrong isotopes because you just use a mass spectrometer to sort them out. You have a magnetic field, you know how large it is, and the protons will go and land, let's say, 2 micrometers next to the deuterons, and then you just sort them out.
I have 2 questions. One is, I guess, you mentioned that basically once the experiment runs at the speed of light, you just put more energy into it. But what is actually the meaning of like the energy that you put into it? What does it change in the experiment? Like the Higgs was found at a particular electron volt.
It was found at 128 giga electron volts. Well, it's more of a philosophical question. There's a way of interpreting the equations of special relativity where you say that when you don't increase the velocity, you increase the mass. But that's just a way of looking at it. It's more precise, and it's more simple to say you raise the energy. And at some low energies, that means that you raise the velocity. And at some high energies, it means the velocity doesn't change anymore. But overall, you add more energy. It's one of the weird effects of special relativity, and there's no very nice explanation.
Let's assume there is an asteroid pointing to Earth. Could you, in theory, point this thing on the asteroid and destroy it, or would it be too weak?
I'm going to help you out, because it wouldn't actually work, because between the accelerator and the asteroid there's the Earth's atmosphere, and that would stop all the particles. But even if there were no atmosphere, no, it would be much too weak. Well, you'd have to keep it up for a long time at least. There was this one accident at the Hera accelerator where the beam actually went off its ideal path, and it went some 2 or 3 centimeters next to where it should be, and it hit a block of lead, just, you know, the heavy metal lead. And the beam shot into this lead thing, and the entire beam, which was a couple of billions of protons, was deposited into this lead, and some kilograms of lead evaporated within microseconds, and there was a hole like pushed by a pencil through this lead block. So yeah, it does break stuff apart, but even if you managed to hit the asteroid, you would make a very small hole, but you wouldn't destroy it. It would be a nice looking asteroid then.
Yeah, before you turn on the LHC, the popular media was very worried that you guys were going to create any black holes. Did you actually see any black holes passing by?
Well, there may have been some, but they were small and they were insignificant. The interesting thing is, sorry, I'm going to the recap, yeah. The interesting thing is that whatever we can do with the LHC, where we make particles have large energies and then collide, is already happening. Because out in space there is black holes with enormous magnetic fields and electrical fields, and these black holes are able to accelerate electrons to energies much, much higher than anything we can produce in any accelerator. The LHC looks like a children's toy in comparison to the energies that a black hole acceleration can reach. And the particles which are accelerated in these black holes hit Earth all the time. Not a lot. Let's say, well, one of these super energetic particles, they come around about once a year for every square kilometer of Earth. But still, they've been hitting us for millions of years. And if a high energy particle collision of this sort were able to produce a black hole that swallows up the Earth, it would be gone by now. So, won't happen.
Maybe more interesting for this crowd, you talked about the selection process of the events. So I guess these parameters are also tweaked to kind of narrow down what a proper selection procedure. Is there any kind of machine learning done on this to optimize? Or?
Not that I know of, but there is a process which is called minimum bias data collection, where you actually bypass all the triggers and you select a very small portion of events, well, without any bias. You just tell the trigger, take every 100 billionth event and you just pass it through, no matter what you think. Even if you think it's not interesting, pass it through. This goes into a pool of minimum bias data, and these are analyzed especially in order to see if, well, the actual trigger criteria are working well. So yeah, there is some tweaking, and even for old machines, we have data collected, and sometimes we didn't know what we were looking for. And some 20 years later, some guy comes up and says, well, we had this one accelerator way back. There may have been this and that reaction, which we just theorize about. So let's look at the old data and see if we see anything of that in there. Now, because it's limited, because it goes through all the filters, you can't do this all the time with great success. But sometimes, in very old data, you find new discoveries, because back then, people weren't thinking about looking for what we are looking now.
Yeah, I always ask myself about repeatability of those experiments, seen as the LHC is the biggest one around there, so there's no one out there who can actually repeat the experiment. So how do we know that, they actually exist, those particles?
That's a very good question. I told you that there is two main large experiments, which is the CMS experiment and the ATLAS experiment. Now, these both sit at the same ring. They have some 10 kilometers between them because they're on opposite ends of the ring, but still, obviously, they're on the same machine. But these two groups, the ATLAS and the CMS experiment, operate completely separately. It's not the same people, not the same hardware, not the same triggers, not even the same designs. They built everything up from scratch, separate from each other. And it's actually funny because when you look at a conference and here's CMS presenting their results and here's Atlas presenting their results, they pretend like the other experiment is not even there. And that's the point of it. They're not angry at each other. It must be two separate experiments because obviously you can't build a second accelerator. So you try to have redundancy in order for one experiment to confirm what the other finds.
Okay, it's midnight and we are out of time, so please thank our awesome speaker.